Hey y'all, Dr. Taylor here, back with you again. I would like to apologize for Chapter 12's podcast. I was having serious technical difficulties. We are good to go now. So obviously this is the last chapter of the class. I'm going to forego Chapter 14 for a couple of reasons. The most important of which is that the main thing we're going to talk about Chapter 13, which is the interpretation of a regression, is basically what Chapter 14 is all about. Anyway, so I just figured, why not? Let's just save you the pain and suffering, and also you should be concentrating more on your research design, which is more important to me and hopefully more important to you. But it is important for this class that you begin to understand and become ever so slightly more familiar with how to interpret a regression. Regression, or ordinary least squares regression, is basically 7th grade math. If you can pass the 7th grade, which you all did, here you are, then you can understand a regression. The issue is making sense of it, given the output that you get from a given regression model, which is what we're going to talk about today. And basically the ideas as well are important. So we're going to scoot through this, and I'm going to switch back and forth between the slides and a tool that I have that I teach another class with that may be helpful to understand gamma and chi-square when we get there. So bear with me as I switch through some different windows, but hopefully this will be helpful to everyone and help you make sense about what's going on. So for today, we're going to talk about measures of association, and we're going to talk about how to interpret statistical tests. And last module you did hypothesis testing. There were some really excellent videos that I found on YouTube from some very smart people about how to understand confidence intervals and hypothesis testing. And so measures of association and the statistics we're going to talk about today are about using hypothesis testing and using different statistics given the situation to tell what the substantive relationship is between your dependent and independent variable. And you can describe the relationship between two variables in terms of the direction. Is it positive or is it negative? The form, this would be general, linear, nonlinear, monotonic. And the strength. And this is what we really care about right here. We care about strength, we care about direction. Form is important too, but strength and direction are crucial, and some of these measures of association tell us nothing about the strength. The direction is fine, but not about the strength. Strength, you need to have a regression, and only regressions will tell you what the strength of a given relationship is. And so we'll also discuss how to determine if a relationship is causal. Which, by the way, I should point out, using quantitative methods, using social science standard quantitative methods in the way that we are, as we know back from chapter whatever it was, in module 3, I believe, we really talked about this, there is no way to tell if a relationship is absolutely 100% causal from quantitative methods. Only experiments can tell us that, and experiments are not always easy to do, which we know. All right. So measures of association indicate the extent to which two variables are related. That sounds pretty straightforward, but it is important that we say it out loud. Each level of measurement has different measures of association. So depending on the level of measurement of most importantly, your dependent variable, depending on how that variable is measured, you're going to need a different type of test to measure the association of your dependent and independent variables. Your independent variable is crucial as well, but mainly your dependent variable. And so this is the table. It is a little less colorful than the one that's in your textbook, but it's the same table. Levels of measurement and statistical procedures, a summary. So this tells you the type of dependent variable you have, the type of independent variable you have, and the procedure, or this is the statistical test you might want to use, or graph, to estimate a relationship. And so here you have quantitative, dichotomous, type of dependent variable. Quantitative here means ratio or interval level. So if you have a ratio or interval level variable, you can use box plots, difference of means, or one-way analysis of variance. Those are called ANOVAs. If you have a categorical dependent variable, then you may need to use different types of analysis, cross-classification tables. These are things like gamma, lambda, chi-square, if you have a dichotomous dependent variable, then you may need to use what's called a logistic regression or a logit model, which we'll not get into, so don't worry about that at all. And then here, finally, if you have an interval or ratio level dependent variable and interval or ratio level independent variables, then you can use a linear regression or scatter plot. You can use a linear regression provided that you have an interval or ratio level dependent variable, regardless. But it's easier if both variables are ratio or interval level quantitative variables. So continuous is another way to say that. So this is just a good little breakdown here. Nothing too crazy to know. It's just that you want to make sure that you are, if you wanted to use this test or any of these statistical tests, you'd want to make sure that you knew why and when you were going to use it. I mean, that's the main idea. So that's where we are. All right, moving on. So let's focus on nominal level variables. So if you have a nominal dependent and independent variable, then you might be able to use what's called a proportional reduction in error interpretation, otherwise known as a lambda statistic. I will tell you that I am a political scientist. I am a professional. I have never in my life ever run across a scenario where lambda has been used. Not to say that it's not helpful. It is helpful. The information that it tells you, the proportion of reduction in error, is important. And it's a crucial statistic in certain circumstances, but it's never actually anything that gives you a lot of information because, again, there's not a lot of information in a nominal variable. These analyses are just really simple compared to what other kinds of measures we have to use to test these things. So lambda is out there. It's important. You should know it exists. You should know how to interpret it, which the book does a really excellent job of walking through that, so I'm not going to go too deep into it. But the main thing is that that this is sort of the first blush kind of test you might use. So, but one that we really care about is gamma. Gamma can be very, very helpful. And these are some other types of measures of association for ordinal level variables. So each coefficient has discordant and concordant or tied pairs, and you basically want to see. So basically, remember, remember that we always have two expectations. All right, you have your null hypothesis, which is that there is no relationship or no difference between the two sets of variables. There's no difference between the things you're testing. And you have your alternative hypothesis or your research hypothesis, which says that there is a difference or that that one mean is higher than another because of some other thing, or that you have some expected difference there. And so with a gamma test, what we are trying to do is we are trying to see, again, the concordant and discordant pairs. And so what that concordant are those pairs that move as one goes up, the other goes up, and discordant would be as one goes up, the other goes down, or vice versa, right? And so gamma, as you see here, gives you a measure of that association. And so depending on your expectations, gamma can tell you whether or not you're on the right track with your research or alternative hypothesis. Should you be expecting that your relationship is positive or negative? And gamma can tell you that kind of information. So again, this is just like lambda. Gamma is a relatively blunt instrument, but it does give you some good information. So we just went over this. But a concordant pair is a pair in which one individual is higher on both variables than the other case. Discordant pairs. So these observations are for variables for two variables for the same observation, right? So an individual or a state. A discordant pair is one in which one case is lower on all the variables but higher on another, and tied is when is in a pair in which both observations have the same value on one or both variables. So again, that's all review at this point. So the problem with gamma and lambda, and before we go back, I do want to this is where I want to take a step back. So I'm going to exit out of here. So how does this work in life? Well, actually, so this is called the SDA database. This is a database that uses real life data from the world, and here is we're going to use the American National Election Study, the NES, from 1948 to 2004 in the cumulative data file. So the NES is a survey that is done every election year, historically. Presidential election years now only, instead of midterms as well. And so every election between 1948 and 2004 is in this data set. And two of the variables we might care about are, I'll just show you here. So this is party ID. Are you a strong Democrat, weak Democrat, independent Democrat, independent Republican, weak Republican, strong Republican, or apolitical? But we only care about these categories because, again, being apolitical is probably just an indication that, in fact, people don't know much about themselves. Because if you really think hard enough, you'd probably come up with whether or not you're a Democrat or Republican. And so that's one thing. And another thing we think may be associated with that is perhaps ideology. So if you have a research question that says, is party ID related to ideology? It's to say, we hear a lot about liberal Democrats and conservative Republicans, but I know that speaking metaphorically, this may not be true. I know in my family there are a lot of people who think they're Republicans, but they espouse liberal beliefs, or they espouse conservative beliefs and they call themselves Democrats. So I want to know what the level of association between ideology and partisanship is in the American electorate in the 20th century. This is what you care about. And so this is ideology. So extremely liberal to extremely conservative, 1 through 7, just like the party ID variable that we have. But the great thing here is that these are categorical variables. These are variables that go 1 through 7. They're categories. And so this is a perfect use of our gamma test. So I've done this already. And the first thing I did was, this is just a simple output that SDA gives you. And so we see a couple things here. So I want to take a second to break this down. So let's go down here to the color coding, because all these cells are color coded. These are blue, these are red. And remember, as we go forward to chi-square, we'll talk more about this as well. But we always have an expected outcome. So this is the overall outcome for each of these. And the row variable is your dependent variable. So let's go back here. So our row variable here is partisanship. So here's partisanship. So these are the expected breakdowns that we have for partisanship. If there was no relationship between partisanship, which we have here, and ideology, then ideology in each of these ideological cells, then we should see about 16% of people across all ideologies calling themselves strong Democrats, because only about 16.3% of the overall public from 1948 to 2004 called themselves a strong Democrat. We should expect, based on this overall total, to see roughly 16.3% in all of these cells. Now, obviously, as you look through here, there's 39.3, and so on and so forth. That's not the case, right? And so this is color-coded to tell us that. And so these are, what are these? Z-scores. And remember, what is a Z-score? A Z-score is a standardized measure. This is from the previous chapter when I messed up the podcast, but the textbook did a nice job. A Z-score is a standardized measure that tells you how many standard deviations a given observation is from the mean. And so the higher your Z, then the more likely then the farther away your given category is from the mean, which means that it's likely a significant finding, right? So that goes back to the previous chapter. Now, here you see that 39.3% of people who were extremely liberal also called themselves strong Democrats from 1948 to 2004. That is much, much higher. That's a much greater Z-score coefficient than those who were extremely conservative. Although it's interesting to say that 40% of people who call themselves strong Democrats over the 20th century were also extremely conservative. Those, I'm thinking, are likely Southern Democrats who are now Republicans after the sort of changeover in the early 90s, the culmination of the Reagan Revolution, so-called. Anyway, again, but you can obviously see there's something like of a linear trend here. You can see the red goes down. Now, one thing we may care about is, well, what about, what's the gamma score? And now gamma ranges from -1 to +1. And so we want to see if as ideology goes up, as ideology increases in number, so ideology 1 and 1 are together, 2 and 2. So 2 is liberal, 2 is weak Democrat. So we would expect that extreme liberals and strong Democrats would be together, right? So we expect that these should be concordant pairs, right? We are expecting a concordant relationship because as an individual says, oh, I'm a strong Republican, we would also expect that individual to say, I'm also extremely conservative. So that would be a concordant pair. This would go up to 7, this would go up to 7. Now again, they're categories, so those have to be very careful about how a category is quote unquote coded, how is it measured. And so, you could flip these, strong Democrat could be 7, strong Republican could be 1. So the number doesn't matter. The number is immediately a placeholder in a categorical variable. And so here, the main point is that with these relationships, we are expecting a concordant relationship. So you can actually look at this in the SD database. Just did another analysis. And this is a graph of what we see here, and so you see very clearly people who say are extremely liberal are strong Democrats. People who say they're extremely conservative are strong Republicans. So that makes sense. But here's our gamma. Here's our gamma coefficient, and some of those other coefficients as well. Here's our gamma coefficient, and this is your lambda here, actually. So this is your gamma coefficient. Our gamma coefficient is a positive 0.41. Now the question is this relationship strong? Because remember, we want to know the direction. So this tells us positive. That makes sense. So as this is what this means is that we have a concordant relationship. As people increase on ideology, they increase on partisanship as well, based on the way these variables are coded. That makes a lot of sense. But the bigger problem is, or not problem, but the bigger question is this a strong relationship? How do we know if it's strong or not? Well, you have to interpret that. There is no measure to tell you if this is a statistically significant relationship, quote unquote. It's all about your argument. You have to know what gamma means to be able to interpret it and then make the case about whether or not gamma is a strong relationship or not. At a 0.41, I'm going to go on a limb and say this looks like a pretty significant, I won't say the word significant, that's a very specific meaning, but I will say this appears to be a strong relationship. Strong Democrats are more likely than other people to call themselves extremely liberal. Strong Republicans are more likely than other people to call themselves extremely conservative. And the relationship between ideology and partisanship is fairly consistent across all categories. Independents break down pretty evenly across all categories. So the main point here is that you have to make the case. It's all about your argument. It's about your capacity to explain what you're trying to say in a reasonable and persuasive way. And if you can do that, then you can use gamma as a way to get analytical leverage on what you're trying to do. What I would have said in the previous podcast, if I'd been able to put it up, was that these statistics are not important because they're statistics. They're important because they give you an analytical tool. They give you leverage on how to make sense of the world in an important way. That's all that matters. And so only to the extent you can make that relationship, use the statistic to demonstrate the importance of this relationship, that's the only value that these statistics have. So, but that's gamma, and that's how you would do it. And so if you just look, you can get a gamma coefficient in some statistical software. But so, all right. So there are some drawbacks. We're using the pairs, but not the actual values of the cases. As a result, different statistics will often give you different results for the same data. So gamma, I will say, often overstates relationships, but I would say that in that case, the one we just looked at, I think that is pretty dead on. Now, another type of test we can use is analysis of variance. Is it appropriate when one variable is nominal or ordinal and the other is interval or ratio? So if you have men and women, and then their feeling. So those are your two categories, and then maybe a feeling thermometer on the president, like whether or not they think, how do they feel about the president. You can use an F test to determine statistical significance there. When we use the Z test, you use the Z table. For the F test, there's an F table. And again, this would be something you would use a statistical software package with. In fact, I'll just go ahead and show you that. If we open up Excel, which I'll do now, I'm doing that. You see the little Excel popping up and down. He's opening. All right, so if we just opened a new Excel, it's like, I don't know. Just a new. How about that? All right, so if you just open this up and you had some data in here, what you could do is you would go to data analysis. This is just using Excel, data analysis, and then over here you have two sample analysis of variance, ANOVA over here, right? ANOVA. So here, Excel will do the ANOVA test for you. The most important thing when choosing a test like ANOVA or correlation or covariance or any of these things, regression is in here as well. The most important thing is to know when to choose it. And so if you were doing an analysis on your own and you thought, maybe my dependent variable is interval or ratio, but my independent variable is nominal or ordinal. Which test should I use? Well, ANOVA may be the test for you. You just want to make sure that you read up back in this chapter and that you work with your faculty member, maybe in a DIS or in the upper level class you're taking, to make sure that you use the right test in that instance. The logic is the same as the Z-test and T-test. It's estimated, the difference of means divided by the estimated standard error. The formula is for small samples. Again, this is Z, the lot that we talked about previously. Z is for large samples, so you could use the Z-test as we talked about before. So one test that is really, really helpful, that a lot of you probably know a little bit about, is called correlation, or it's a lowercase r. And correlation is a measure of strength and direction of the linear correlation between two interval or ratio level variables. It ranges from 1, just like gamma, 1 to -1, and just like gamma, 0 means no relation. So gamma, in a sense, you could think of it like this. Gamma is a correlation for categorical variables, and correlation is correlation. And to use correlation, you need to have two continuous, or let's just say interval or ratio level variables. Now, 1 is perfect positive association, -1 is perfect negative association, and 0 means no relationship. And so this is a great graph, a great table from your textbook that shows you the relationship here. So these dots are your given observations for your dependent and your independent variables. So this is some variable that you care about, and this may be the expected presidential percent of the vote for the incumbent party, and this may be GDP or something, and so this would look something like that. So as GDP goes up, of course the scale will be different, but as GDP goes up, the expected two-party vote share for the incumbent party goes up as well, and so that's a very strong correlation at 0.99. You might say here, oh, this is both a strong and positive relationship. For -8 point, and again, how do we know it's strong? And we don't know. Just like gamma. They should have points down there. That's irritating. Just like gamma, or decimal points, I should say. Just like gamma, making the case about strength of relationship with correlation is difficult because it's up to you to interpret that. So we know that correlation ranges from 1 to -1. So if your correlation coefficient comes back at 0.99, you might say, shoot, that's pretty good. That's almost perfect. That's a strong relationship. -0.98, is that as strong? Well, I don't know, not as strong, but it's still pretty strong. So, the question then is, which one of these is better? Well, it doesn't really matter which one is better, so-called. It just matters that you're able to describe the relationship and that your theory and hypothesis, as these two variables are related, makes sense, and that this demonstrates some analytical leverage for you to make the case about the strength and direction of the relationship. Is it what you hypothesized? Is it not? Can you reject the null or not? Actually, that's difficult to say. We don't know. There's no significance test here. So we don't know if we can reject the null. But this does give you evidence that further exploration is warranted. Now, the moderate... Oh, shoot. Sorry, guys. I did it again. Now, moderate correlation is... again, how do we define moderate? Again, mainly because this would be 0.52. So we know that the relationship ranges from 1 to -1. So again, make up, to your standards, you have to make the case. And then a weak relationship here is getting close to 0. So anything above or below 0.20 to -0.20 is probably going to be defined as a weak relationship. Anything above 0.25 or below 0.25 to about 0.6 could be considered moderate and so-called. But those are just numbers I just came up with the top of my head. I mean, that's just my experience and my own interpretation of this information tells me those things. If you wanted to make a different case, you could do that. And that's why knowing why you're using some of these statistical tests is important, so that you can make the case for yourself about what kind of relationship you think exists and why. So that brings us to chi-square. Chi-square, like gamma and lambda, is used for categorical variables. Now, chi-square is a little different in that chi-square can actually be used for interval ratio level variables if your dependent variable is categorical. Although chi-square can also be used for categorical variables in both instances. So chi-square is very helpful. This statistic essentially compares the observed result with to the expected result that we thought we were going to have, right? And so if there was no relationship between the two variables you have, then the expected outcome in all categories should be what we get in the overall outcome. So if that sounds familiar, that's because it is. So stated differently, the chi-square measures discrepancy between frequencies that actually observed from those we would expect to see if there was no population associated between the variables. So let's go back to our example over here. So this gives us a chi-square statistic. So our chi-square value, when we could go to the back of the book, there's a chi-square critical test table back there. You can look at that table, you can get the critical value, but I'm just going to go ahead and tell you that a chi-square test statistic of 5,805.19 is larger than any critical value in the back of the book, even with 36 degrees of freedom. It literally just doesn't matter. So this is a significant result, and in fact we have a p-value here, so the p-value is lower than 0.00, and that's obviously, this is a significant finding. But what does it mean? What this chi-square is telling us, this goes back to these rows here. So this row is what we expect. We expect that 16.3% of all people consider themselves strong Democrats. 13.1% of all people consider themselves strong Republicans. And then you can go through each of these rows and do the same thing for each of these categories. So if there was no relationship between ideology, which is what this is, ideology, and partisanship, which is over here, then the categories across ideologies should be the same as the overall category for this as the expected value for the sum of each of these partisan categories. But that's not the case. And so we can see this. For one, we can use z-scores to see that. 2, and then 3, if all else fails, chi-square gives you sort of a holistic understanding of what's going on. But note, this is an important thing about chi-square. Chi-square just tells you about the overall relationship between these two variables. It doesn't tell you, like we could see in that table that we were looking at, we could see differences between liberals and conservatives and strength of those ideologies and relationships. We could see a lot of different things going on. The z-scores are helpful there as well. But all the chi-square tells us is that the expected values we thought we had between partisanship and ideology are different than the observed categories. We observe something different than what we expected. That's all that it tells you. And that we observe something differently enough than what we would have expected, that it is a significant difference. And so that's what chi-square tells you. So chi-square increases as the departure from the observed and expected frequencies grow, which is exactly what I just said. So that's pretty much all chi-square tells us. And that's helpful, but again, it's sort of blunt. All right, expected frequencies in each cell of the table are found by multiplying the row and column marginals and dividing by the sample size. All right, so we didn't have to do all that. It's in the book, but usually your statistical software packages are going to give you that output. But here's a chi-square. I mean, we could do the analysis here. So we would expect, that excuse me. We would expect that do not put up extreme differences, and this variable here and the total observations would not differ by category, but of course we do see they differ, and so we might have a significant chi-square finding. So we could do the simple math like this. So you could take each of these cells and then do the simple chi-square math. This would be your chi-square value, and then you get your degrees of freedom in this way, which this is on the textbook, so I'm not going to belabor this point. And what we end up with is a test statistic, or the critical value of 16.18, and the test statistic that we had was 55.66. So obviously the test statistic is larger than the critical value, so there is a significant finding, right? So you can reject the null hypothesis. So it's chi-square. All right, so let's talk about regression. So what's important to me is that you are able to interpret this regression. And regression is a tool for describing how strongly and under what conditions an independent variable and dependent variable are associated. This can be used to make somewhat causal inferences. Because in a bivariate, let's just say two-variable relationship, you are not accounting for possible issues of spuriousness. Now, of course, theoretically, you think that you are. You think that your dependent and independent variables are importantly related, but you're not accounting for everything. And as long as that's the case, then you're always going to have some sort of possibility to introduce spuriousness. So we can make somewhat causal inferences. So the ordinary least squares regression formula is as follows. By the way, if anybody remembers y equals mx plus b, then this is the same thing. And so this is the expected value of your dependent variable. This is your y-intercept, or where the regression line is estimated to cross the y-axis. This is your slope, and then this is your independent variable. And if beta sub yx is positive, then the relationship is positive. Sorry, guys. If it is negative, then the relationship is negative. So this sign here becomes important. So this is exactly the same thing. This is a linear model. And this is, again, if you went through the 7th grade, excuse me, I have a tickle in my throat. If you went through the 7th grade, then you definitely know. Oh, I have water back here. If you went through the 7th grade, then you definitely know how to interpret this information. The question is, can you interpret it using these variables? When I was in 7th grade, I remember my mom was an 8th grade math teacher, so I was always very irritating in class. And I remember thinking many, many times and asking my teachers, in my math classes specifically, because my mom loved math and all this stuff, I kept saying, when am I ever going to use this? I loved history and social studies, and obviously I'm a political scientist, so there must be something there. But I said, when am I ever going to use this? And God bless them, they did their best to try to tell me when, but they never could explain it. But let me tell you right now, you're going to use this for the rest of your life. And you say to yourself, wait a minute, Dr. Taylor, that's crazy talk. You don't know me. What are you talking about? I'm not going to be a political scientist. That's fine. This model, a linear regression, is everywhere in your life. It is in predicting the stock market. It is in predicting housing prices. It is in predicting job creation. It is in predicting and understanding political relationships and economic relationships and social relationships. It's in psychology. It's in sociology. It is literally everywhere. Literally everywhere. And the more familiar and the more comfortable you are thinking about the world in these terms, and the better off you're going to be as you move forward through your career. In the 21st century, if you've ever been in my class in real life, and you'll have heard me say this, but I'm going to say it now, we're online, doesn't matter. In the 21st century, what a college degree gets you is a ticket to a job where you will be asked to analyze data and information. That's what a college degree gets you. No matter what your major is, that's it. So the better you're able to do that, the better off you're going to be. So, regression, what it does, what this formula is doing is providing the quote-unquote line of best fit that minimizes the distances from each data point, and the line minimizing the squared error. So you can look back. Let me look at your book right here. I mean, you can look back in chapter 13 and you can see these examples they've got all through here. And you know, I mean, it's not important to me that you know the ins and outs of the math behind these things, but it is important to me that you're able to interpret this information. And so basically, as long as you know that we're trying to create a line that minimizes the distance from each data point, then we're good to go. And so this is a way to think about it. So this is your dependent variable. This is your independent variable here. So you're on a given observation. You have an observed variable here for one observation, and that same observation has another variable observed here, and those two data points meet here. Well, there are 50 other observations in this data set, perhaps, and they've all got various and sundry y and x observed values. And so from those, we can create a predicted y value. This is called y hat. Y hat. And so y hat is a predicted value, y sub I is the observed value, and y bar is the mean that we have. And so, and this, as this line goes down, this is your y-intercept, I should say. And so what we're trying to do is we're trying to create a line, this line here, that, imagine there are lots and lots of data points all throughout here. We're trying to create a line that goes through this cloud of data, creating the smallest amount of error between the observed and expected values, right? Or predicted values. This is your error. And so we are explaining this much about the world, because this is our mean for this set of data, and this observation is way above the mean. So we're trying to explain, because of x is trying to explain why the regression runs so much differently than the mean for a given observation. So this is what a regression line does, and so that's what we're trying to interpret. And the great thing about regression is that this is the first time you can get to substantive effects. To interpret a regression, for every 1 unit change in x, you get a subsequent slope change in y. That's what we're saying. Right? That's what we're saying. For every 1 unit change in x, you get a slope change in y. That's what it means. So there can be problems, though, interpreting regression when you have data that have outliers. So, for instance, surgical procedures by surgical specialists in Allstate District of Columbia, 1987. And so, you know, here you go. And this is surgical specialist per capita. And so what you see here is DC. They have a lot of surgical procedures done and a lot of surgical specialists. I guess a lot of people in DC are having plastic surgery. I have no idea. But anyway, and so the main thing, though, is DC is an outlier, and so taking DC out changes the entire nature of this relationship. So it's barely sort of marginally negative here, but it's fairly moderately strong here. So taking into account outliers is always important, just like with measures of central tendency. Because we're working with the mean is sensitive to outliers. Remember, mean is very much a part of regression. You have to know what the mean is, and it's going to be involved in the variance and things like that. So as a result, then regression can be very sensitive to outliers. You have to be aware of that. You have to be aware. So the issue is for us to figure out how to interpret a regression. So imagine that you have this output. And so when you have a regression, you're going to have r squared, and a slope and a y-intercept. So a couple things. This is r, and r squared. What r squared does, r squared tells you the percent of the variance and the dependent variable being explained by the model or your independent variables. And so here in this situation, our r squared is explaining about 7% of the variance in the dependent variable. We have 10 observations. It gives us 8 degrees of freedom. Our slope is, or our slope intercept is, so for every 1 unit change in x, we see a 0.244 increase in y. And our y-intercept is 2.89, and our standard error is 0.304. And so we have a couple of questions. How would you interpret this? Is there a statistically significant relationship between the independent and dependent variables if we're going to use the alpha 0.05 and we're going to use a two-tailed test? So how do we do that? Well, let's walk through it a little bit. Well, the R tells us that there's a weak positive relationship, okay? R squared tells us that we're explaining about 7% of the variance in y, which we talked about that a minute ago. And so the slope tells us for an increase of 1 unit in x, the independent variable increases our dependent variable by about 0.244 units of y, whatever those units are. So this is where your unit of analysis becomes very important. You want to talk about these findings in the measure of the variable. So if we're talking about for every 1% increase in the approval of the presidential candidate, they receive an additional 0.244% of the vote. I mean, something like that. You have to talk about it in the nature of the variable. And then the predicted value of the y-intercept is 2.896 if there was a 0 for the independent variable, right? There was a 0. Which actually that makes sense. If you have an approval rating of 0 and you're running for president, I would suspect you get probably about, 2.89% of the vote. Sure, that makes a lot of sense. Actually, I'm interested to know that worked out. So the question becomes, how do we know if it's significant or not? Well, we can use a t-test. We use a t-test. And so a lot of statistical packages will actually give you the p-value of a given relationship, and what they're doing is they're cutting out this process. And so if you wanted to know if a relationship was significant, you could interpret it as follows. You take the slope of the relationship, so 2.44 right here, and you divide it by the standard error, right? 2.44 divided by standard error, there you go. And that equals 0.83. This is your t-test statistic for this variable, this relationship. So then you go to the back of the book, you get your critical t-value for 0.05 with given degrees of freedom at 8, right? So, and this would be in the back of the book. Let's look and find it together here real fast. So if we're looking at the back of the book, Appendix C, nope. Appendix D, nope. Appendix, must be Appendix A, but that would make sense. That's Z. Oh, one-tailed test, chi-square. Chi-square distribution, F distribution. All right. Well, look in chapter 12. I know we have this in chapter 12. Yes. Chapter B, 606. You know what? My book does not have the T, critical T. Oh man, that's stupid. But anyway, so what we know is that the critical T, I will give you a critical T table for this assignment that you're going to be doing in this module. So if you look at the critical T chart, you'll see that for a one-tailed test, a 0.025, which gives you a two-tailed test for 0.05, but for a one-tailed test, 0.25, degrees of freedom of 21, you would need to get your critical value at 2.080. So obviously, if you look at the critical T, you'll see that our t-test statistic is not larger than critical T, which is here. There's a critical T from that. But it's so obviously, if your t-test statistic is not larger than your critical T value, then it is not a significant relationship. And so that's it. But you can still interpret it. So for a 1 unit change in Y, you get a subsequent, 1 unit change in X, you get a subsequent slope change in Y. That's the interpretation. So you can interpret that forever. You can put a 5, put a 10, whatever. Put it in there. And so one of the questions we might have is, all right, how do you interpret this in real life? So Lee Epstein and a few other people have put together a database where they measure the ideology of Supreme Court justices and the ideology of presidents on economic ideology. And so they measure this from 0 to 100. So they have two continuous interval ratio level variables, and they plot the line here. And so what we have is a linear regression of that relationship. And so here we go. So this would be Y hat actually. So the relationship that we see here, this is from your textbook by the way, is they have a slope of 37.69. So on average, if a presidential ideology, if there's the most conservative president in history was a 0, put a 0, so presidential ideologies, put a 0 in right there, then all of a sudden this slope becomes a 0 as well. And so that means that the y-intercept, 37.69, right there, would be the expected ideology of a justice on on economic issues if their nominating president was the most conservative economic president you could be. So similarly, if you put a 100 in here and be the most liberal you could be, it'd be 100 times 0.34, so you'd add 34. So you'd end up somewhere over here, right, in the mid-60s. So you just add like 34 to 37. So you'd end up like 67 over here. And so that's where you'd end up. That's why this line is way out here. And the question is this a significant relationship? And so you would divide. I don't know how many observations there are here, but we've only had 45 presidents, give or take. So you'd put you get your T critical value or critical T value, and then you would divide 0.34 by 0.13, and then you see what that gets you, and then you'd see if that value was larger than your critical T value, and if so, and by the way, it is. I think critical T is 0.196, and then this is larger than 1.96, and so that means it's a significant relationship at the 0.05 level, and so that's how you interpret it, right? It's just that simple. That's it. And this is a bivariate relationship, so we're not taking into account everything. We could take into account more, but that's where we are. So this is it. This is the last one. So in this last module, you do some interpreting some relationships, and then you are done. You are done for the semester. Really excellent job. Keep working on your research designs. Get those literature reviews done. Check out chapter 15 if you want some help on the research design write-up. And I've had a great semester. I hope you have as well. If you watch this before the 15th of June, which is a couple days into the module, so you probably haven't, but if you do, make sure you do your course evaluations. You'll get it, if everybody does it, if enough people do it, we'll get an extra 3% on everybody's research design. All right, so Thanks a lot, guys. I've had a really good time this summer. I hope you have too. Send me an email if you have questions or problems. See you later.